Hi, my name is Dylan Rudelsky, and this is Lab 3 of Physics 2211, the black hole in orbits. For the introduction, the purpose of this lab was to first record and analyze movement around a black hole in order to calculate its mass of the black hole, and then figure out the initial velocity for a spaceship to achieve a figure-8 orbit around a planet and moon. The fundamental physical principles that we used were the position update formula, the velocity update formula, and the gravitational force formula. Here are the results. I found the mass of the black hole to be 1.67 times 10 to the 34 kilograms. The image on the right shows the path of the spaceship around the moon and the planet, and you can see that the spaceship is circling the moon while orbiting the planet, which results in the figure-8 pattern on the two of them. The second image is the orbital path of the sun around the black hole, with the masses of the black hole listed underneath. The average of all the simulated masses is what gives us the mass of the black hole. For the lab setup, this lab was entirely simulated. The first simulation was of a black hole that had a sun orbiting around it. We had to use the orbit in order to calculate the mass of the black hole. The second simulation was of a planet, moon, and a spaceship. We had to write the forces acting on the spaceship and the moon in order to figure out how their movement would be affected by each other. We then had to plug and check different initial velocities for the spaceship in order to find one that gave us a semi-stable figure-8 orbit around both the moon and planet. Here are the simulated orbits shown again, closer up. Here are the important codes. You can see the seed, that was my email, and then this is the code. Here's the important code for part 2. This is the initial ship speed that we were editing, and this is the position and force update formulas that I mentioned before. The first part was easy since it was just plugging in all the equations to solve for the mass of the black hole using the force of gravity equation. The second part was more difficult as I had to update the force, velocity, and position of both the spaceship and moon while figuring out which initial velocity gives me the figure-8 pattern. I eventually found out that an x component of negative 1.7 times 10 to the 4th meters per second and a y component of 43,000 meters per second gave me the orbital pattern I was looking for. Possible sources of error. The figure-8 orbit likely degrades after a certain amount of time due to picking a random velocity, and taking the mean of all given masses for the black hole might not have been the best way to figure out its mass. What does it mean? Discuss how the net force and its parallel and perpendicular components are different from the rate of change of the momentum and its parallel and perpendicular components. These components are actually equal. The rate of change of momentum parallel is equal to the net force parallel, and the rate of change momentum perpendicular is equal to the net force perpendicular. What if? If you wanted to predict the motion of the entire system, what would you need to include in your computational model? Think about all the interactions in the system. Would there be any dominant interactions, or would they all contribute more or less equally? If you wanted to calculate everything, you would also have to include the mass of the black hole and the mass of the sun. However, the dominant interactions would still be the planet and the moon, as the spaceship is far closer to those than it would be to to the sun or the black hole. Which means that the black hole and sun, while they do contribute in a far less noticeable way than the planet and moon do on the spaceship. Thank you for your time.